Okay, this game got a little bit crazy. I'm not gonna spoil it, but you know, this got really crazy real fast. Okay, so guys, it's been 10 months I didn't make a video on any channel of mine. School has killed me, and I actually stopped doing YouTube for a long time. I think this is the longest break I ever took from YouTube. But honestly, now that it's summer, I wanna get back into it. So without further ado, I will start this video. Hey guys, and welcome back to Nico Dev. Today our objective is simple: create the worst chess AI ever, meaning the chess AI that will try to play the worst moves in order to lose as fast as possible. But not only they have to play as bad as possible, they also have to react to the opponent moves and pretend that the opponent also wants to lose. So they have to find the best moves to lose in contrast to their opponent. So this is gonna be pretty funny, and we're probably gonna break a bunch of stuff doing this, so let's get started. Anyway, what you're seeing right now during the intro is actually a game that I played against a random guy on chess.com. I wasn't logged in, so you cannot see my name, but I was playing the white pieces, and I think I did a blunder like in the middle of the game, like I blundered my queen, but he also had lost his queen. I think I could have won like in the middle of the game, but then I did something dumb. But in the end, I managed to succeed, and the game is gonna end right now. And okay, after flexing my epic chess abilities, we are now gonna try to create an AI that lacks these abilities, or like it's the opposite of these abilities. But yeah, leave a like if you enjoyed the video and want to see more content like this. Perhaps we can do other chess AIs that do random stuff, just like taking en passant every single time. And if you guys don't know what en passant is, it's basically a glitch in the matrix where a player can basically hack into the game and eat a piece when a piece is not actually there. It's insane. And we can force an AI to do that. Or also we can do an AI that plays the bomb cloud, so it can actually play an opening that a lot of chess masters play. I mean, at least 2 chess masters have played this opening in an official event. Now you would say, Nico, you're a genius, you're creating an AI from scratch. No, okay, I never said I was gonna do that. We are gonna be using Stockfish. You know what Stockfish is? If you don't know, it's fine. I mean, if you're not into chess, it's alright, I'm not judging you. But basically, Stockfish is a source code, an open source free chess engine that will basically try to find the best moves and play chess as best as possible. There are a bunch of iterations of Stockfish. It actually gets updated pretty recently, so it's actually pretty good. And it's one of the most known chess engines before Alpha 0. It also has like built-in neural networks into it, but we're not gonna be using them because like that is gonna complicate stuff a lot. And also it's probably gonna tinker with our plans because the neural network will probably try to win instead of losing, so we're just gonna disable these. But anyway, I will go through how this works like generally, because there is a bunch of code, and then we're gonna try breaking it in order to actually get an AI that does what we want, which is like literally the opposite of what anyone else would want. So this is gonna be a really exciting video. First of all, let's download the Stockfish thing from GitHub. All of the links are gonna be in the description anyway, and also all of the links to all of the games that I play in this video, except for the intro one, which I already deleted because I wasn't thinking about it. Okay, so this is the Stockfish thing we downloaded. We actually only need to work on the source folder, and here we have a bunch of scripts. Now, it actually took me a while to understand what the change was gonna be that I was gonna do in order to actually break this and make it do the opposite of what we want. And we're gonna explore these scripts in a while, but for now, let's just compile and see what this chess engine is actually able to do. So compiling the engine is actually pretty simple. You just have to open a terminal here and then write make build, and this is like the way you want to build it. But yeah, I found this on the internet, so I have no idea. Anyway, it's gonna make a build, and as you can see, it's generating all of the compiled files because this code is written in C++ and in C, as now it's generating the binaries, and then we can use these binaries to actually, make the chess engine work. Anyway, while it's doing this, I just wanted to say, if you don't know how to play chess, this video is probably not gonna make much sense. So like, I'm gonna link in the description like a 1-minute video that just explains the basic rules. You can just watch that if you've never heard of chess before somehow. But yeah, I'm not judging. Anyway, this is now over. It generated all of the files, and as you can see now we have a runnable, which is Stockfish. And now we could just do execute Stockfish like this, And as you can see, we will go into like right now we are into Stockfish. I believe there are some commands, I don't remember them. If you do position, I don't know what the commands are. Okay, let me look at it in GitHub. Okay, it's D for displaying the position. So if I do D, as you can see, it will show me the position. Oh, okay, so you can type in a position like this, but we just don't care about the position, we just want the starting position, and then you have to do go. Okay, and then it will start analyzing the position, so it will tell you what the best move is. Yeah, as you can see now it's saying, yeah, E2, E4, and also D2, D4, and like the basic openings, and I mean, naturally, it's the start of the game, so the position is pretty much equal. Actually, it's gonna be slightly better for white, but you know, that's just an expert thing. Anyway, so as you can see, it's suggesting this move, and now we're gonna know this is the move, and then we can input it in, and this is basically how the engine works. Okay, but naturally, this is a really bad way to actually use this engine, and it's gonna be really hard to input moves. So what I did is I downloaded an app for Linux, which is called Pichess, which basically is able to make AIs fight each other. So I can just load a new game. So what we can do is go edit engines and then disable this engine and add our own, which is right here in, okay, what is this? Okay, here in download Stockfish Master, and this is it. So now we have our engine, we are gonna load it, and I believe this is all fine, we can load it in, we can create a new game, and bam, and oh, okay, no, I wanted maximum difficulty, and play normal chess. And now the two engines are basically gonna battle each other. And as you can see, everything is fine, because we didn't change anything about the engines, and naturally they're gonna be really good at the game. One thing you have to understand about how this works is that every time there is a new position on the board, the engine is gonna analyze the position, it's gonna give a score to that position, and then it's gonna try to find the best move, so the move that has the best score. So the move that transforms the position in a position with a better score. And that's basically how it works. And as you can see, they are doing it. They're playing chess. It's happening. Okay, this is actually some good chess. I mean, it's kind of weird because it's played by engines, not real people. So you're gonna see some weird moves. But still, they're playing chess. Okay, well, I am not a chess master. I don't know what to say of this. But yeah, I can say this is pretty entertaining. Anyway, real chess is boring. Okay, we want them to play some actual like non-boring stuff. Okay, and that's what we're gonna do right now. So let's close this. And let's close this Reddit page I was using for help, and let's actually take a peek into the code. So the first thing I noticed is that there is an evaluate function or class, and basically this file takes care of evaluating a position. So I was thinking, what if we evaluate the position backwards so that it's gonna do the exact opposite of what we want? And I was searching through this file because there is a bunch of code that I don't understand. And so it's evaluating the position in a bunch of different ways. I guess if it finds a bishop or a knight in a certain position, it does something. This is actually really well commented, but still it's really hard to read. So one thing I noticed is that this score variable is getting used a lot, and then it's getting returned. So the first thing I tried to do was actually to multiply the score by -1, so the value that gets returned is actually the negative value. So if you guys don't know how the score evaluation works, if you have black pieces, you get a negative score, and it means you're winning. If you have white pieces, positive score, it means that you're winning. So if we do multiply by -1, basically when white is really winning, the AI will think that black is winning, so it will try to play the worst moves in order to make this score the opposite. I don't know if this makes sense. So like multiplying by -1 might just do the trick. Unfortunately, I tried this on my own and it literally does nothing, like it doesn't affect anything for some reason. Or like it tinkers a bit on how the engine works, but doesn't do very significant damage. And the reason being that this score is actually being returned a bunch of times, on different occasions. So we need to find a way to actually change this score somewhere that is getting retrieved all the time. So the next thing I found was this function right here, make score. And as you can see, if we go into this function, we go into it, we will get in this class, which is types.h. As you can see, we have a score, and this function right here actually generates a score. It takes two integers and it returns an integer. And now we finally understand what a score actually is. A score is a merge of two different integers, which are the middle game score and the end game score. And this is the reason why multiplying the entire score by -1 didn't give the behavior we wanted, because we were actually multiplying by -1 a compound integer, which was basically the merge of these two integers right here. So let's try to understand what this code is doing and let's try to reverse it. So let's use our beloved GIMP and actually think about this. Now this is gonna be really bad because I'm really bad at drawing with my mouse. I mean, anyone is, let's face it. Okay, so, okay, this is good enough. Okay, this is okay. So we have two numbers, mg and eg, and it's generating a new number by doing this operator right here. Now if you don't know what this operator does, it basically shifts all the bits of one number to the left 16 times. So let's imagine we have a number right here and it's supposed to be 16 digits long, but you know, just because it's hard to actually type right like this, let's make it 4-digit long. We have two numbers right here, okay? And this is the middle game and this is the end game. So the number that it generates is basically the middle game number, so this one, and then it shifts to the left the end game number by 16 places. But in our example, it's just 4 places because the numbers are 4 of length, so it's gonna put him right here. And this is our full score. So what we want to do is somehow turn this number and this number into a negative. What I noticed is that there are two values that actually return both the end game value and the middle game value. And also I have no idea why it's actually putting them this way. I guess it's for optimizing because, you know, Stockfish, it's gonna be really hard on execution, and so optimizing the things like this is gonna help a lot. So these two functions actually extract the end game value and the middle game value, and we actually want to reverse both of them. So the simplest thing that I tried doing was actually reversing both the end game and the middle game by just adding a minus both times. So this way, every time a function is trying to get the score, it's actually gonna get the reversed score. Okay, and that's the only change I wanted to make. Let's try building again and let's see what happens. Now, while this is building, I actually wanted to talk about another thing, so let's do another board right here. Now, what I wanted to talk about was the Minimax algorithm. Because you guys might say, okay, Nico, why are we doing this? Why are we changing the score? Couldn't we actually keep the same scores, but just instead of taking the higher number, we take the lower number? So, like, let's say that the engine finds 100 moves, okay? Instead of taking the best one, we just make it take the worst one. We just reverse it. Why couldn't we do that? Isn't that easier? So the reason we can't do that is because the engine is actually not finding all of the moves. It would be too hard to find all of the moves. So as it says on this article right here, after the second pair of turns, there are approximately like almost 200k moves, 200k possible games, so there is no way an engine can go through them all. And this is only after 2 moves, I mean 2 pair of turns, so that would mean like 4 moves or something. And after 3 moves, it's gonna be like 121 millions, so that's crazy. So how does an engine like Stockfish actually work? I mean, it's probably a lot of optimizations and stuff like that, but the main optimizer that actually makes all of this possible is the Minimax algorithm. So the main optimizer for Stockfish is alpha-beta pruning, and I'm gonna show you what I mean right now. Okay, so let's say that this dot right here actually represents a position, okay? Just a position in the game, or it could be the starting position of chess. This position can lead to a bunch of different positions, and this can lead to a bunch of different positions. Okay, it's really hard to explain it like this, let's just use another app. Okay, consider this circle to be a position, okay? This is gonna be position 1, or like the initial position of chess. This position is obviously gonna lead to a bunch more positions. It's actually like a lot of positions right at the start because you can move all of the pawns and all of that stuff. But let's pretend there are only 2, okay? And naturally in this first position is gonna be white to move, and in this position is gonna be black to move, so let's mark them as black. And let's actually keep going with this tree for quite a while so I can, you know, share the example a little bit more. In this position is actually gonna be white to play. And then it's again black to play. Now, how many positions the AI can actually explore, so how far down it can go down the tree, is called the depth of the analysis of the engine. In our case, it's Stockfish. Now, a depth can be like a number that is anywhere from like 12 to 21, it could be any number. Naturally, the more depth the engine has, the more precise it's gonna be, but also the more time it will require. And in this example, the depth of the algorithm is actually 4, because we are going 4 steps down the line. This is the initial position, 1, then it's gonna go to the second branch of the tree, which is 2, then 3 and 4. Naturally, this tree could expand a lot more, and you could reach more and more positions, so you can see more and more into the future. Now, once you reach the bottom of your tree, so the bottom of your depth, you're actually gonna analyze these positions. And as I said before, Stockfish actually returns a score that goes from negative to positive, negative if black is winning, positive if white is winning. So let's analyze all of these positions, meaning let's just implement random values. Okay, so let's say that this position is -6, this position is 7, so white is winning, this position is 3, this position is 4, this position is 1, this position is 5, this is 6, and this is 3. Oh, okay, well, I guess I typed a 2. I guess it can be 2, it's fine. So, okay, right here it's white to play, so naturally white wants to get a positive score, because remember, positive means that white is winning. So white will definitely go for this move, which is 7. So we could say that this position right here is also valued 7, because white is not going to choose anything else other than this path. Then right here we could do the same reasoning and say that white is going to choose 4. And this is the max part of the algorithm, because we're getting the maximum value out of the ones we are prompted with. Now black needs to do the same reasoning but backwards, because black actually wants the lowest score possible, because remember, negative score or lower score means that black is doing a better job, the position is more in favor of black. So in this case, black will actually try to get 4, will try to minimize the score, so as you can see it will go down this path. And we can quickly do this for this path as well. This is going to be a 5, this is going to be a 6, so this is going to be a 5. And now white knows that in order to win or have a more favorable position, they have to go to the right, because this actually returns a better score for white. So this evaluation is going to be 5. So what's going to happen is that the algorithm is going to go down this path right here. We can mark it in red. So it's going to go right here, then it's going to go here, and in the end, if both players play at their best, they are going to reach this position right here. And then naturally the algorithm will keep on going and, keep analyzing stuff and keep doing this job. Now this is the Minimax algorithm. It's called Minimax because naturally there is one branch where we try to maximize the score and then the next one where we try to minimize it. So it's just doing max and min functions all over and over in a recursive fashion. But now, as I said before, analyzing all of this position is going to be a mess because, as it was said in that article, after a few set of moves, this branch right here is going to contain like millions of elements. So it's going to be really hard to analyze all of those positions. So there are many optimizations, but the main one is alpha-beta pruning. Basically, what alpha-beta pruning is we should actually go back to the example before. Okay, so at the beginning, we don't know anything about the position. As you can see, there is a sad face. We don't know, like, literally anything. Then we have a few question marks, I don't know. Okay, so the first thing that the engine does, of course, is go at the bottom of the branch and analyze a few positions. Okay, let's pretend that this position is going to be -3, at example, and this one is going to be 2. So naturally, the next step is going to be evaluating this position, which is still going to be 2. Okay, so far so good. It's the same as before. We did no optimization. Now let's try doing this branch. Now let's pretend that this is gonna be 5. Now we could go and analyze this position as well, but if you think about it, we actually don't really need to analyze this position at all. The reason being is that we already know that this value right here is gonna be higher than 5. I mean higher or equal to 5. You may say, Nico, why is that? Well, because if this position is a 3, then naturally white is gonna choose 5 because this is higher and white wants the highest score. If this position is a 7, then white is gonna choose 7, which is the higher score, but white will never choose a number that is lower than 5 naturally. So even if we don't know what this is, we never evaluated this position, we know that this number right here is gonna be higher or equal than 5. Now let's go back to this position right here. Black actually wants to find the lowest move. Remember, black wants to minimize the score. So if black had to choose from going to 2 and going to a number higher than or equal to 5, which path would they choose? Well, naturally they would choose the lower number, which is 2. So without needing to evaluate this position right here, black already knows that they have to go this way. This is the main optimization that allows us to not analyze all of the positions, but just some. Unfortunately, because of this optimization, we have to do some extra work, because if we only wanted to revert the positions that were analyzed. So let's say that the engine has analyzed all of these positions, okay? And instead of taking the best one, we take the worst one for white because we want to reverse the chess engine algorithm. Well, that wouldn't work because actually the chess engine hasn't analyzed all of the position because it missed this one. So this one could also be the worst position ever, and in our reversed algorithm we would actually want to go here, but since this position was never analyzed, our broken engine, the engine that we want to create, is actually gonna go here. And naturally, white is supposed to get the best move, but I'm saying in the modified version of our algorithm, it will try to go to the worst move. But the worst move is actually not this, but it's this one. We just don't see it because the Minimax algorithm and its optimizations have, removed the need to actually find this position right here. So this is why it's much easier to actually change the score rather than changing the position we pick. The way we could fix this is actually reverse the algorithm. So instead of it being a min-max algorithm, it would be a max minimum, where white is actually trying to find the worst move and black is trying to find, white is actually trying to minimize the score and black is trying to maximize it. But that would need to change a bunch of stuff in code. So I thought, okay, just reversing the scores of the evaluation is gonna work. Because basically in our broken engine, all that is happening is that the algorithm is exactly the same, but instead of having -3, we have 3. Instead of having 2, we have -2. Instead of having 5, we have -5. So right here the situation changes, because instead of it being higher or equal to 5, it's actually higher or equal to -5. And in this case, the optimization actually doesn't work, because naturally, black doesn't know if it's better to choose the right path or the left path. Because it depends. If the right path is lower than 2, then it's better to choose this one. So you would need to analyze this position, which is gonna come to something like, I don't know. And then this is gonna become -5, and then it's actually, black is actually gonna try to go this way, as opposed to this way. And this is basically how it works. So yeah, I hope I really didn't confuse you, but I just wanted to briefly explain this, and there are other tutorials that talk about this as well. I'm gonna link them in the description. But now I think our chess AI actually has finished and we can actually test it out. Okay, let's start a new game. Let's go to edit engines. Let's remove our old engine. Let's go to our new fancy one. There we go. And actually we want to disable neural networks because I have no idea what this code does and it's probably gonna try to fix itself. So let's disable neural networks, and let's also disable this file right here just to make sure. As you can see right here, there are also a lot more settings that we can tinker with. We're not gonna go through any of these, but these actually worry about the depth of the algorithm and all of that stuff. Also, there is this 50 move rule, because if you guys didn't know, in chess, after 50 moves where a piece is not captured or a pawn is not moved forward, you're actually gonna end in a draw. So this optimization actually tries to make that not happen. But again, we don't worry about that. I guess we can keep that on. And without further ado, let's create a new game of our Choose Stockfish, unlimited time, and let's start the game. Let's delete this game, and there we go. The two engines are gonna try to start battling each other and actually lose. Okay, yeah, I mean, we can already see some weird moves going on. And you can see that the scores are all reversed, so like one player is trying to win, the other one is trying to lose really badly. As you can see, he tries to blunder his queen. But the beauty of this is that, as you can see right there, okay, it was really quick, so it was hard to notice. Right here, white actually put this queen here, not only because they wanted to lose it, but also because black doesn't have any other move. Like literally black, since they are in check, they are forced to take the queen. So they are forced to make white give up material, and that is what I was talking about before. It's not only trying to find the worst move, but it's trying to find the worst move that actually makes it, that actually their opponent can't deny. So it's the worst move no matter the outcome of the opponent. So let's go forward with the game, and as you can see, white also sacrificed the queen, and this still keeps on going. And this actually takes a while to settle in, and it takes a really long time, and at the end the game always ends in a draw, because unfortunately there is no way to force a player to checkmate the other player, so it's always gonna end either in a stalemate. I actually had a few games where there were like 7 queens on the board or something crazy like that, and then it ended in a stalemate. I'm gonna show you a few games now before ending the video, but before this there is actually some optimizations I still want to do. So changing the minus sign is not actually enough to make the algorithm behave weirdly, even if it looks like it's working. Because the problem is, in the end game, it's actually gonna try to win, and we don't want that. So let's close this game. So I ended up changing 4 different classes, and I'm gonna show you the changes. It's actually pretty minimal, but it actually helps also in the end game. So what I did right here is, instead of changing the negative sign of these 2 functions that we changed, I actually created 2 different functions for inverse, okay, and I actually changed where the functions were getting called. So this function right here, these 2 functions are exactly the same as these ones, but there is a negative sign, so they are being multiplied by -1. And the reason I did this is that sometimes you're actually getting the values multiple times, and so it would actually multiply by -1 twice, which would actually, you know, return the good value. So I didn't have to use the inverse functions all the time, but only at the very end. And so right here in the evaluate function, as you can see, instead of taking the mg value and the eg value, I'm taking the inverse on both occasions. So I changed it in a few other places too, as you can see right here, basically at the very end of the chain, because sometimes it would get the score multiple times. And as you can see right here as well. Oh, okay, right here as well. Okay, it's a bunch of places. Okay, and the last place is right here. Oh, see, I think this code is actually for the rule 50 moves rule. So, I mean, this is probably not gonna come really useful, but still, it's nice to have. Anyway, I also changed something in the pawns script. I have no idea why. Oh, it's always the same reason. I changed the mg value with mg value inverse and mg value inverse. And finally, I changed something in the search algorithm, because the problem is that while searching for a good score, it was using the evaluation. When you actually had a mate, it would actually, so mate means that you can win the game in a certain set of moves, no matter what the opponent does. So once you actually had a way to win 100% for sure, then it would actually start using a different min-max algorithm with alpha-beta pruning, as you can see. And so this is why at the end of the game it would win for no reason, it would try to win for no reason, because of this freaking algorithm that was trying to find the best move. So what I did is I reversed the algorithm. So as you can see, where it was written max, it became min, and then from min it became max. So instead of being a min-max algorithm, it's now a max-min, but only when you find a mate with certainty, so only at the end of the game really. And now, thanks to this, we can have 2 AIs that battle each other and try to lose as fast as possible, but they both try to lose, so it ends in a draw. And this is basically all of the stuff I changed. I don't think I changed anything else, nope. So yeah, I didn't need to change that much, and I'm actually gonna push this on GitHub as well, and make a fork and just call it like bad Stockfish or something like that, so you can check it out in the description. Okay, and before ending the video, I actually have some matches right here that we played Bad Fish versus Bad Fish, which is basically our AI. Then I tried to play the AI, but I tried to lose, and then I tried to beat the AI, so we're gonna try to look at them right now. So you can actually export games as PGNs, and basically what they are just simple text files which contains the move. And as you can see, this game is really simple because I tried to beat the AI, which is really like not something difficult, since we tried to make the AI you know, the easiest possible to beat. So if we import the PGN, this is basically the game I had. I just put out my queen, and I did a good old scholar mate, and there you go, he got checkmated. But then we had more interesting games, like this game at example right here. I tried to lose against the AI, and as you can see, in the end it resulted as a draw. So let's load this game in, and bam. And okay, well, spoilers, okay, why did you start by the very end? And the reason I'm showing these games after the fact is because it really took a really long time to generate them, because I didn't want to stress the AI. I actually wanted to find the best moves, so we could get the best results. And as you can see right here, I tried to blunder my queen, but it actually doesn't take it. And I'm like, take my queen, okay, and finally he takes my queen, but then he blunders his queen. And as you can see, the game continues, and he blunders some of his pieces. As you can see, when I take pieces, I'm actually forced to take. I don't have any other move, so it's actually making a really good job at losing right now. As you can see here, it forces me to take the queen, the rook. There is actually no other move that I can do, so it's really doing a really good job at making me stuck, and I'm doing a really bad job at anything else. But I mean, no matter how much he tries to lose the game, it will always end in a draw, because, you know, there is no way that he can force me to checkmate. Probably there are some positions where it's possible to force a player to checkmate the other. I actually don't know. I mean, we have to talk about too expert about this. I don't think there is a way. So I think it's always gonna result in a draw, unless you do something really stupid. And as you can see right here, he's technically losing because he has less materials on the board, but there is nothing that I can do. And he knows that. And that's why, you know, it's resulting in a draw, and then I'm just gonna blunder a knight because, you know, it's a draw anyway. There is no way I can, he can force me to checkmate with this configuration. Okay, and finally, the game you all been waiting for. Oh, I opened it with the wrong thing. No, I wanted to open with a text file. The game you're all been waiting for, Bad Fish versus Bad Fish, and here we go. Okay, this game got a little bit crazy. I'm not gonna spoil it, but you know, this got really crazy real fast. So it begins like a normal game of chess where the players just blunder their respective queens, and this is fine, this is really fine. I was actually surprised that White hadn't lost their queen so early, and it actually blunders a lot of pieces in the middle of the game, which is not good. But afterwards I actually see White's plan, I think at some point, because I think White is trying to get his knight stuck or something, so that they can blunder it. So yeah, this is really confusing. This went on for a long time. This game was so long. I mean, it was so boring how long it was. But at some point, I think, yeah, at some point, White takes the rook. I have no idea why. It could be because the Stockfish already knows it's a draw, so you know, it doesn't really care. But it could also be because, I don't know, the rook might help to free the position a little bit, but I have no idea, so that the other pieces could be forced to be taken. But I don't know, I have no idea, but I mean, the engine knows, so you know. Also, another thing I noticed is that when the engine promotes, it's always a queen. I don't know if it's something like, it's definitely not hard-coded, but maybe it has a tendency to promote to a queen all the time, and I didn't change that. Or maybe also they promote to a queen because it's the easiest piece to give away, because laterally you can just do this, and then the king is forced to take. He doesn't have any other move, so maybe that's why they promote to a queen, but I don't know. And as you can see, he keeps doing this, and then he keeps doing this, and he doesn't know what to do because he cannot checkmate. Like, he could literally just do this and it's checkmate. Oh no, actually, yeah, I mean, then he does this and it's checkmate. No, that's stalemate. Okay, like this and it's checkmate. And he doesn't do it because naturally he doesn't want to checkmate the opponent because he wants to lose. And so, without knowing what to do, he just keeps on making queens. And I'm guessing it's also, you know, at some point it's gonna stalemate because of the 50 moves rule. And the bot already knows that naturally he cannot win, aka he cannot lose, and he just keeps trying to make queens, and this goes on for so long. I literally left my PC on and went to eat, and this was still going, and keeps going, and then I think it's a draw because of the 50 moves rule. Yeah, it's been 50 moves without any captures or pawns advanced, so you know, it's a draw. So yeah, this is the perfect worst game. It's really interesting. I'm gonna leave all of the PGNs for you to download, as well as the entire project if you wanna check it out. I'm gonna fork the Stockfish project. Naturally, I'm not gonna take the credit for it because Stockfish is such an amazing product and there are so many people working on it, and that's the beauty of open source actually. And I'm really great to be doing my part and actually, you know, working on improving it with quotation marks. And okay, I'm joking, but yeah, this was a really good project to work on, and I'm really excited to be back at making videos. And honestly, as I said at the beginning of the video, I had this idea for a while and I really wanted to make it happen, but you know, kinda school got in the way, and finally I'm done with my exams, by the way. I'm completely out of high school, so next year I'm gonna go to college, and it's gonna be actually quite interesting to see the developments of all of this and all of my YouTube channels. This said, thank you so much for hearing me ramble for a really long time. Honestly, I don't know how you did it. And yeah, jokes aside guys, thank you ever so much for watching the video. Leave a like if you enjoyed it, and I'm gonna see you guys in the next one. See ya!